So our goal is to develop the double integral for polar coordinates, and what we're going to show is that if we want to think about the double integral, actually it's written down below so I won't recopy it. Well, no, I guess we'll write it down here. We're going to show that if we're going to evaluate a double integral in polar coordinates, that we could first rewrite that as the double integral over r of, well, I'm sorry, I should stick with what I was going to do. And we'll just put it up here. So if we have some f of r comma theta, and this part should look familiar. There's nothing different here, right? It says to take some z value, multiply that by some amount of area. So a height times an area gives you a volume, and then you think of this double integral as adding up over both those variables. And so that's going to give you the volume for the, you can imagine that being either the total volume or the net volume for that surface that lies above this polar region. Okay. So we saw this in the pre-work, but again, if here we had some surface lying above, not above the xy axis, but above our polar plane, we take some region, and we could talk. What we're talking about is finding a way to interpret, either the volume of that column that I just drew, the volume of that shape that I just drew, or the net volume of it if it dips below and above the polar plane as we draw that. Okay. So what we're going to find out is that this is equal to the double integral over r of f of r theta, and the key thing that I want to derive today is how are we going to interpret this dA, and the answer is it's going to be thought of as r dr d theta, and it's imperative to me that you understand, one, where this r comes from today, two, that you're on the lookout for it as you're just solving these problems, because you can't do them without that extra factor of r, and three, that you begin wondering if there's a way to generalize this to doing substitutions to other coordinate systems. And if that's the case, is there a way to come up with this r faster than what we're doing today? And that will be the culmination of this chapter 16, is where we show how to change coordinates to any sort of coordinates and figure out what other factors would we need there if we're doing such a change in coordinates. Okay. But for right now, we're just interested in how could we get that r just by breaking up this polar region here, just like we did in the rectangular coordinate system, and seeing if we can figure out where that r comes from. Okay, so the first thing I want to do is So the first thing I want to do is I want us to think about, we're trying to find what I want to find now is the the area of the kth rectangle. So we want the area of the kth rectangle. So I said before that this isn't really a rectangle, and I kind of want to exaggerate it slightly. So maybe we could make the region look something like that. So this is what I'm calling so I'm calling this the kth rectangle. But as we said, we're in polar coordinates here. That's not really a rectangle. Those aren't right angles at each other, but that's our polar equivalent of a rectangle. And so the first thing I want to look at is, okay, so this is going to be stemming from some polar axis right here. And so I'm going to put dashed lines here like this. And if we, so one way we could look at this is, coming from our polar axis, this region is this kth rectangle looks like this, where it's bounded on one side by some r equals r sub k, k minus 1, and some r equals r sub k. So it's got a radius on either side of it. Okay, just like we had x of k minus 1 and x of k, and y of k minus 1 and y of k to describe this region. We're now doing it with, we've got 2 radii and 2 angles to describe this region. Okay, and then here we have this theta k minus 1, and this would be theta k here. Okay, so that's our kth rectangle, and we want its area. Okay. Again, because it's not rectangular, I can't simply just take delta. I can't take, don't write this down, I can't take delta theta k and multiply it by delta r sub k, because that would only work if this were a true rectangle where you could truly take length times width. Instead, the way we want to look at this is we want to look at it as the area of two different sectors. So here, I don't want to mess up that drawing, so let me just kind of recopy it here. So the way we'll think about this is we'll think about there being an outer sector. So I'm going to trace the outer sector here in black. That's the outer sector. And then we have inside of there, which I'll do in green, we've got the inner sector. So rather than thinking about trying to calculate a rectangle, what we're going to do is we're going to calculate the area of the outer sector and subtract from that the area of the inner sector. Okay. And we'll do that here in just a second, but then the next thing I want to talk about is once we've got the area of the kth rectangle, how are we going to develop our notion of net volume over this? So let's jump there first. So the first thing I'm going to do is from within inside that kth rectangle, we need to pick a representative point. We need to pick some r k star theta k star from within there. Okay. And for the time being, because this is the best way to develop this by hand until we get more advanced techniques, we're going to think of that as being the midpoint of this region. So remember way back when you did Riemann sums in Calculus 1, you did the left endpoint method and the right endpoint method and the midpoint method. And eventually you said, well, if this limit exists for any one of them, it exists for all of them and it's the same thing. So it turns out it doesn't really matter which method we use initially in our approximation. If the limit ends up existing, it's the same thing no matter what we pick. So for the time being, we're going to pick the midpoint. So what's the midpoint? Well, that would be the coordinates. We're going to, if we're picking the middle r value, we simply take the average of the two radii. So that's r of k. I'm going to write r of k plus r of k minus 1 just for how this is going to work out here. So again, if this is my, let's see here, this is our r of k minus 1 and this is our r of k. If I want to be midway in between there as far as the radius is concerned, I add the two together and divide by 2, right? That gives me that halfway point in between them. Okay, and then what will my theta k star be? Again, I want the middle theta value. So this is given by some theta k minus 1. Ooh. And this is given by some theta k. And so my theta k star is just, again, going to be the average of those two. This isn't actually going to be necessary, the theta k star, for what we're about to do. But we are going to need this description. So keep this description in mind here as we go through this derivation. Okay. So once we've got that, we're going to say that we're going to approximate the net volume is approximated by the sum from k equals 1 to n of f of rk star, comma, theta k star, so times our dA. So this part should look very familiar at this point. You've done this a number of times, both in Calc 1, Calc 2, and now a couple times in Calc 3, where we're saying we're approximating some sum that represents, some total, in this case, the net volume, but it could have been net area under the curve or something like that. What we're saying here is we're going to take a height times, and in this case, a small unit of area. And so that in total gives us some volume, and we're going to be adding them up. So there's nothing new there. That part should look completely familiar, except that I'm using r and theta as opposed to x and y. Okay. But again, oops, I'm sorry, I want to write this as, I wrote dA there, that's bad notation. I should use delta A sub k. I'm sorry about that, folks. So I just changed that on you, but I just underlined in red, I just changed on you. Instead of using differential A, I should use the size of the the size of the kth rectangle. Okay. Okay, so now we're ready to finish this out. Which room do I have left? Okay, so my area of the kth rectangle, so think of that, so we'll just label that, that's the area of the kth rectangle. Again, I'm using that word rectangle very loosely. But
what is the description underneath where you just wrote in green for net volume? What does that say? I can't.
Yeah, I'm sorry. That says a small unit of area, or a small amount. Was that your question, Cedric? Did I get the right one?
Yeah.
Yeah. Thank you. Okay. So our delta A sub k is going to be, as we just said, so I'm looking for the area of this kth rectangle right here. And so that's going to be the area of the outer sector minus the area of the inner sector. In your pre-work, we re-derived something you've probably seen before, but if you've forgotten or maybe you've never seen it before, we re-derived how to find the area of a sector of a circle. Okay, so that makes our a sub k, delta a sub k, or the area of that kth rectangle. It's going to be 1/2. What's the area of the outer circle? Well, the area of this outer circle is 1/2 times. So, just to recap, the area of a sector we derived last time in our pre-work was 1/2 r squared theta. So the area of the outer sector is going to be 1/2 r k squared times whatever that angle, the angle spanned by these two, which is theta k minus theta k minus 1. That's the area of the outer sector. Anyone have any questions on that? I could see where you might have a question on that. So. Let me just point, because if you're just going off of what I did in the video, when we talked about the area of the sector, we first just drew a theta starting from theta equals 0 up to some theta equals something else. So maybe this is theta k. So then we only had, for the area of a sector, we only had that the area of the sector was 1/2 r squared theta k. But if I were doing this for some other sector that wasn't starting at, let's say we were looking at this slice of the pie right here instead. So here we'd have some theta b, and here we'd have some theta a, and so our total theta would be theta a minus theta b. So the area of this sector would be 1/2 the radius squared. That part hasn't changed, but what I'm saying here is we'd have theta a minus theta b. That would give us this net theta for the area of the sector. Is everyone okay with that? Okay, so at this point what we've said is the area of the outer sector, so the one that I traced, see I traced it in black here. I forget whether you guys can see, could you guys see that pen tip as I do that? Or do I need to, maybe I'll put my mouse there. So this outer circle here, or that outer sector there, that's what we just found right here, the one that I traced in black. Thank you, Allison. Minus the area of the inner sector, which is going to be 1/2 r sub k minus 1 squared times our theta k minus theta k minus 1. How are we doing? Okay, so what we can do is we can do a little algebra here. We'd have 1/2, and then I'm going to rewrite this as maybe a big bracket, r sub k squared minus r sub k minus 1 squared. So I've got a difference of perfect squares there, times theta k minus theta k minus 1. Okay. And then for the last step, I'm going to factor this difference of perfect squares. So that gives me 1/2 r sub k plus r sub k minus 1 times r sub k minus r sub k minus 1 times theta k minus theta k minus 1. So folks, we gave the area of the outer sector and we subtracted from it the area of the inner sector. That will give us the area of this red, quote, rectangle here. So the area of a sector is 1/2 r squared theta. So we did the difference of those two, and now I'm just doing some algebra. I had rk squared minus rk minus 1 squared, and I factored that difference of perfect squares. And here it is, folks. This expression right here, what can I do with this?
Isn't that your r sub k star?
That's our r sub k star, right? If we do the midpoint method, that's just our r sub k star. And so we've got r sub k star. That's what I defined right there. And then I'm just going to replace this now with delta r sub k and delta theta sub k. So finally then we could say that this sum over here then is the same thing as the sum from k equals 1 to n of f sub rk star theta k star, then rk star delta rk delta theta k. Okay. And so then what we do is we're going to define the double integral over r of f of r theta dA. We're going to define that to be the limit as, I'm just going to put delta goes to 0. I don't really want to talk about that unless you want to. As delta goes to 0 of the, so that think of that as the, you can think of that as like the diagonal of that kth rectangle. F sub r theta, r k star theta k star, r k star delta k, or delta r sub k, delta theta sub k. Okay, so folks, there we've derived the double integral and polar coordinate systems, and while that's kind of interesting in its own right, where it's more important is how we're going to use it. Hey folks, if you got a lot of stuff going on in the background, if you wouldn't mind muting your webcam, I'd appreciate that. So what we want to use this for is if we've got some function that's continuous in the rectangular coordinate system, how could we shift this or transition this how can we do a substitution to put this into polar coordinates? And so what we'll say then is, given some rectangular region, this is a rectangle as far as R is concerned, or as far as our region is concerned in the polar coordinates, then we can go ahead and say, here's our substitution. This is the integral from theta equals alpha to theta equals beta of the integral from r equals a to r equals b of f of, and then I'm going to do the substitution that we've always done when we substitute into polar coordinates. This is going to be my r cosine theta, comma r sine theta, and then here's the r dr d theta. And it's absolutely essential that you not lose track of that r dr d theta. If you do a polar substitution and you don't have that r dr d theta, you haven't actually transformed it into the polar coordinate system. Okay, so let's go ahead and work an example now. So for number 3, we want to find the volume of the solid bounded by this surface and the xy plane. So we're going to start off in the rectangular coordinate system again, and this is the conical quadric. And so if you imagine its shape, it will look something like this. Okay. So folks, I never expect you to sketch I shouldn't say that. That's a little bit bold of a claim. But I don't generally ask you to sketch the graph of the surface living above the xy plane. But what you do need to do is you need to sketch your xy plane and see where that surface either intersects it or where it gets projected down onto the xy plane. So you need to sketch what I'm saying here is you need to sketch your region R here. So if let's see, this is x, this is y, so here's y, here's x. Okay. So what does this look like? Well, if I want to know what this looks like when it lands in the xy plane, what I can do is I can set z equal to 0. So that happens when 4 minus the square root of x squared plus y squared equals 0. And if we were to solve this for, I think we can see now what this would look like, but let's go ahead and solve this for x squared plus y squared. So if I solve this for x squared plus y squared, I'd have 16 is equal to x squared plus y squared. So in the xy plane, this is just the circle, x squared plus y squared equals 16, and so our region R is the interior of that circle. Well, I shouldn't say the interior, but it's that disk, solid disk. Okay. So folks, whenever you have a scenario where you're describing your region in a circular format, it may be helpful to translate this problem from a rectangular integral to a polar integral. Okay. I won't say that it's always going to be the case, but it will often be the case. So if you see an x squared plus y squared or some sort of combination of that, you may want to think about trying to put this into the xy plane. Into the polar plane. So now I'm ready to go ahead and do this whole substitution that we talked about. And if so how would we describe this in the polar coordinate system? So now we're going to do what everyone does, which is kind of a abuse with notation, I guess, but we're going to go ahead and put the polar coordinate system right on top of that to talk about it. So, how would we describe this region? Not as the rectangular region that's given by this, interior to the circle here, but how would we describe this as a polar region? We'd say that R is equal to the set of R comma theta, and this is what you guys did in your pre-work, such that, and then let's see here, we're describing this circular region, and we could just say, so we have 0 is less than or equal to R, which is less than or equal to, and the radius of the circle is 4 here. And what would our theta values go from to describe? This is enough to describe this, but we'll just go ahead and say that theta is ranging between 0 and 2 pi. Okay, so we can go ahead and set up this double. So the original double integral was double integral over R of this f of xy dA. But now we can go ahead and write this as the integral. So we're going to write this now as an iterated integral in the polar coordinate system. So I'm going to write this as, let's see here. We need to go ahead and rewrite our function in terms of the polar coordinates. So that's going to be 4 minus r. Is everyone okay with that, or do you want me to talk about that substitution that we just did? Thank you, Allison. So folks, this is our function, right? That's the function that we're integrating over our region R, and we've transformed that into the polar coordinate system. Is everyone okay with that? Okay. And we have r dr d theta under the substitution that we just talked about. Now, what are our angles running from? Or sorry, what's everything running from for describing this region? We're going to describe it from r equals 0 to r equals 4, from theta equals 0 to theta equals 2 pi. So any questions, folks, about how we just transformed this into the polar coordinate system?
I think I have a question.
Yeah, go ahead.
It looks like the original equation was 4 minus the square root of x squared plus y squared.
Uh-huh.
And r squared equals x squared. Okay. I think I can see how you did 4 minus. I was going to say, why did you do 4 minus r instead of 4 minus the square root of r, but I think I know why you did 4 minus r.
Okay, yeah, so one thing I didn't do here was actually write out the substitution. So here is our substitution. Okay, so we're going to let x equal r times the cosine of theta, y equals r times the sine of theta on our region R. And so because of that, so we'd have that x squared plus y squared then is equal to r squared, so we could rewrite this f of r theta as 4 minus the square root of r squared. Okay. But because we picked positive values for our r, or I shouldn't say non-negative values for our r, when we have the square root of r squared, we could just write that as 4 minus r, and that's what I put in here. Excuse me.
Well, we need that 0 to 2 pi parameter on tests, or is the r from 0 to 4? Okay.
In describing the region, that's fine because there's only one way, that's fine for describing the region. But when it comes time to putting the limits of integration on your iterated integral, you do need limits of integration for the theta values. You don't have to write theta equals, but you would still have to have thetas ranging from 0 to 2 pi.
So as long as it's on there, it doesn't have to be in the region R.
That's correct, yeah.
Okay.
That's fine. And by the way, so folks, one way to think about this is we're going to go out, we'll go out a fixed theta value, and so let's say we're at like this particular theta here. So we go out to a fixed theta value, and then we, all along this theta line here, we give ourselves different r values. At each then r comma theta pair, we evaluate that in the function. And then we move the r value along until we've summed up over that entire ray, and then we adjust our theta, moving further along to another ray, and then we sum up along that. So that's how that fits with that same notion of an iterated integral that we saw in the rectangular coordinate system. Okay, so let's finish this out. So in this case, this is the integral from 0 to 2 pi of the integral from 0 to 4, and I'm just going to rewrite the integrand as 4r minus r squared dr d theta. So that's the integral from 0 to 2 pi of, and then integrating this gives us 2r squared minus 1/3 r cubed, evaluated from 0 to 4 d theta. Or we end up with the integral from 0 to 2 pi, And let's see here, that would be 16, 32, and that's 64 minus 64 thirds. So let's see here, 96 thirds. So I think that's 96 thirds minus 64 thirds d theta, 0 to 2 pi, and that would be another 32 thirds. Okay, double check me on that. So then integrating this, we get 32 thirds theta evaluated from 0 to 2 pi, and that gives us 64 thirds pi for that region. Okay. So one interpretation of that is if we've got this function, if we think of this function as living over the xy plane, then we've got this conical shape surface, and if we want to find the volume between the xy plane and that surface, we've just found that it's 64 thirds pi. Of course, folks, what could you do with this problem? Well, this is a nice geometric one, and you probably could check this against your volume of a cone formula. Okay, so I'd like you guys to go ahead and set up this next one, give this a shot. So one thing that I think would be very helpful is to sketch your region. I find that people that are successful with these problems are those who've sketched their region before they start trying to do the integral. Just go ahead and sketch the region and then try to set that up, and we'll start up here. Well, we are going to do some that are strictly in the polar coordinate system that will be in some ways a little bit harder. But yeah, the whole point of this tool isn't that, well, it's to build a more kind of a larger theory that says, hey, if you're working with an integral and it's hard to integrate in a particular coordinate system, it may be easier to integrate in a different coordinate system.
Okay.
And so these are cooked up, but if they didn't have something like an x squared plus y squared in them, you may not have any desire to convert it to the polar coordinate system. It may not make your life easier.
Okay.
And so we could start, oh, go ahead.
Sorry, you can finish what you're saying. It's just a quick question.
So I was going to say that you could certainly convert any integral to the polar coordinate system. It doesn't have to have an x squared plus y squared, and it's just a question of, did it make your life easier by moving it over to that coordinate system? And unless it, there's a few kind of common indicators that it may be easier to do that, and one of those is that just seeing an x squared plus y squared component. There may be others, but that's kind of the big one. Yeah, Phoebe.
Okay, for my bounds for R, is it going to just be 1 to 2?
Yes.
Okay.
Yep.
Okay, cool. Thank you.
Mm-hmm.
I have a question.
Mm-hmm.
This seems so simple, but I don't know how to get that picture.
Did you do this one in the? Did you work through the pre-works on these?
Yes, I did the pre-work.
Okay, so we know that the equation x squared plus y squared equals 4 gives a circle of radius 2, right?
Yes.
And we know that the equation x squared plus y squared equals 1 gives a circle of radius 1.
Oh, that's a plus sign. Okay, I get it now.
Okay,
Sorry.
yeah, that's no worries. So we've got two disks here, and so we're looking at we call this an annulus, but then when I say that the x values have to be greater than or equal to 0, that just is the right half of that annulus. Great. And then our y is equal to our sine of theta. Okay, so let's go ahead and set up our new integral in polar form. So the double integral over r of f of x y dA, we could write as the iterated integral in polar coordinates from theta equals minus pi over 2 to theta equals pi over 2 of the integral from r equals 1 to r equals 2 of 1 over 1 plus r squared r dr d theta.
Could you just as easily, instead of putting theta equals negative pi over 2, could you do, I think it's, can you do 3 pi over 2?
No, you can't. And the reason why is up here we put a stipulation on the way we develop this, and so I would just say let's just stick to the script, which says that we have to have the upper limit of integration, and I think I'm actually missing a 0 here. Let's just say 0 is less than or equal to, well, actually just strictly less than beta minus alpha, which is less than or equal to 2 pi. And so this says that the difference between the two, the upper and the lower, has to be a positive difference, which means the upper one has to be greater for the way we develop this. There's probably other ways you could do this, but because of the way we made some assumptions probably implicitly as we were setting this all up, always assuming that the thetas went from, were in order from least to greatest, positive values from least to greatest.
Okay, thank you.
Yeah. Okay, I think in the interest of time, I'd like to just move on. Does anyone have a burning desire to see this one solved out? Okay, so this would use some sort of u substitution because we've got that factor of r here. So we'd let u equal 1 plus r squared, which makes du equal to 2r dr. And then we could take, 1/2 du would be our r dr, and then we could go ahead and do the substitution here and keep going. Okay, let's go ahead and look at another example. Okay. So just like we saw before, we started off in our rectangular coordinate systems by only working with a region that could be described by a rectangle, a true rectangular region. And then we said we'd like to do this for more general shaped regions. We can do the same thing here where we imagine talking about our region looking something like this. Let's see here, if you see. We'll go ahead and do x and y, but we'll put our polar axis over this. And so maybe we have some curve here that's some h of theta, and some curve here that's some g of theta. And we're going to do this between, some theta equals alpha and some theta equals beta. So the difference here is now the upper and lower curves are not just strict radii. They are some, we think of the r as being some function of theta. Okay. So we're not going to do any work to derive this. We'll just go ahead and do it if it works out just like we did for the rectangular coordinate system. And so how would we find, let's see, well, first of all, if we had a continuous function that was bounded by the region I just described, then how would we go ahead and evaluate it? If it was a function of f of x, y, then if we put it into polar coordinates, that's how we could evaluate that iterated integral. And the thing here is, just as before, the upper and lower limits of integration, like we saw in the rectangular system, are functions of theta. or functions of the other variable, I guess is what we saw before. And this part, I just went ahead and put it here because it fit well, and that is if we want to just talk about the area of the polar region. So in this case, if I just want to compute this area and not think about some surface living above it, then I just replace this with a understood 1, and that double integral will compute the area of the region in the polar plane. Okay, so let's practice both of those. So for number 6 here, we're asked to set up an appropriate iterated integral in the polar coordinates for calculating the net volume for some g of r theta. We're going to assume that it's continuous on our region, and what do we mean by our region? So we're going to consider, first of all, the first time, well, in both cases we're going to have the same curve, so let's go ahead and sketch both of these. So again, folks, most of us are more comfortable thinking about this as x, y, so we go ahead and think of this as the x, y coordinates as being superimposed on top of this, even though we're talking about r as some function of theta. Okay, so this is the circle r equals 2. And then we have the other circle, which is given by so this is the circle r equals 4 cosine of theta. Okay, so we've got these two boundaries, I guess, and we're going to go ahead first think of the r as being the region that is exterior to r equals 2 and interior to r equals 4 cosine theta. So for this first example, this will be our r. So here's how I want to make sure, you know, and you probably saw this in Calc 2, but I just want to make sure we think of this the right way. When we integrate and we're running through our values of r, so let's just take any old radius pointing out here. We're going to start counting the radius of values when we hit that boundary, and we're going to stop counting the radius values when we hit that boundary. So I imagine this radial arm sticking out, and we're going to start counting the radius boundaries when we hit that lower boundary. So we don't have upper and lower here, right? We have inner and outer, I guess is what I'm trying to say in our polar coordinate system. Okay, so let's go ahead and set this up. So our double integral over r of, we're using g here, of g of r theta dA is going to be the double integral. And let's see here, we're going to sweep these radial arms starting at 1 theta value and stopping when we get to this theta value right here. Does that make sense? Do you guys want to see that a little more in depth? So I'm going to run out this radial arm. There's nothing, there's just a point there. Then I'll scoot over my theta, and then I'll run along this arm here. Then I'll scoot over my theta, and I keep scooting that theta over, and each time then summing up for different r values within this region. So what we need to determine is when do we start summing, where our theta start and where do they stop? Well, the theta will start at the intersection, or the theta will start and stop where those two curves intersect each other. So we need to figure out where is this point here. And that point occurs just like we did in our rectangular coordinate system. We're going to set the two functions equal to each other. So I set the two radii, the blue curve and the red curve equal to one another. So this happens when the cosine of theta is equal to 1/2. And that happens where? Well, when is the cosine of theta equal to 1/2? On the for the region we're looking at, and this is where, again, you get in a lot of trouble if you don't sketch the region. If you just trust a calculator, or if you don't have a picture that you're looking at, you can get a lot of trouble because there's lots of cosine values that will output 1/2. But for our, what just happened? For our concerns, we've got theta is equal to minus pi over 3, and then theta is equal to pi over 3. This is where theta is equal to minus pi over 3, and up here this is theta equals pi over 3. So we're going to start our theta values ranging from minus pi over 3 up to pi over 3. And then now we're going to look at, well, how about these radial arms that I talked about? Does everyone see what I'm pointing at? Maybe I'll make a bigger picture of that. So what I'm thinking of is I go to a fixed theta, right? Let's fix some theta. So here we've got, this theta right here. And when do I want to start summing up the values in the region? Well, I want to start summing them up when my r gets to here, and I want to stop summing up when my r gets to here. So this radius is what? Well, that's just the radius r equals 2. So that's our lower limit of integration. And we're going to stop when we get out to here. And that's when the radius is equal to what? Well, that's on this second curve here, the one I've traced in red. That happens when r is equal to 4 times whatever that angle is. So that's when r is equal to 4 times the cosine of theta. Let me make that a little bit neater. I'm just going to delete it and make it a little bit easier to read there, folks. Oops, and then that was r going from where did we first start entering that region? At r equals 2. And where did we exit that region? We exited at r equals 4 cosine theta. And then we've just got our g of r comma theta, and then times r dr d theta. So folks, absolutely make sure you've got that r dr d theta. That's the classic mistake for these types of problems. Okay, great. So then for this next one, we want to consider our r to be interior to both circles. So I'm going to sketch this once, and then we'll switch over to the sketch that I took from the book, because I'm sure I won't do a very good job of this. So again, one more time, here's the circle with the radius of 2, and then here is the circle centered at the point 2, 0 with the radius of 4. Okay. And this time what we're looking for our region is this region right here. Okay, I'm going to draw on top of this here in just a second, folks. So just as before, we're going to have the question of, what angles are we going to be sweeping from. We also want to be talking about the radii here, because what we find is that this is sort of like the regions in one of our regions in the xy plane, where at some point we change which curves on top, and so we have to break this up into subregions because we've changed the upper curve. The same thing here is happening if you think of these radial arms as going through the region that we sketched. Notice that the lower radius is always somewhere on this well, it's always coming from the pole here, but our upper radius changes. So for example, if I could zoom in on this real closely, so here for this radial arm right here, and that's a little hard to see, and I apologize for that, but notice that it's coming from the pole, that's where r equals 0, okay? But it stops when it hits the red curve. As opposed to if we have a radial arm extending through here, we're going to start again at r equals 0, but we're going to stop when we hit the blue curve. Does that make sense, folks? Okay. And so there's this third region up here that we have as well. Okay, so now we've got a zoomed in picture of this. It gives us our 3 regions. So you can see here's that kind of cat's eye that's formed by these 2 circles. And so we've got this first region, which I'll call R1. this second region, which we'll call R2, and this third region that we call R3. All of this together makes up this green region that I originally sketched. Okay. Okay. So we'll go ahead and set this up, and we'll say that the double integral over the region R of g of r comma theta dA, that's what we're trying to compute here, right? We can break this up into 3 subregions. So that's going to be R1, g of r theta d theta, or excuse me, dA, plus R2, g of r theta dA, plus R3, g of r theta dA. And why did I have to break this up into 3 different regions?
Because like your upper and lower bounds basically
On the
are
what?
changing.
The upper lower bounds on what?
Like if you were going around counterclockwise here, at one point it's just like a part of a circle, but then you can see at right there at that bottom like teal line, it changes. There's a hard point where if you were going around, it changes. Your upper bound not on your theta, on your r.
That's what I'm looking for. The upper bound on your R curve changes as you swing through this region. So sometimes the upper bound is this curve right here, and sometimes over here it's the second curve. Okay, so that's why we have to break this up into several regions. Great. So for the first region that I've labeled R1, okay, notice that these intersection points still haven't changed. That's still at minus pi over 3. That's at theta equals minus pi over 3, and that's at theta equals pi over 3. So those intersection points haven't changed. Okay. But for that first region, we're going to integrate this from what to what? Well, so notice that I'm going to start drawing these. What angle am I going to start drawing these radial arms at? And I really wish I could make this, a lot bigger. And let me exaggerate that first region slightly. Okay. So that's at theta equals pi over 3. That's that first region here. I've changed the way it looks. That's that this little half sliver, almond sliver, I guess, of a region. When did the angle start? So the angle certainly is going to stop at minus pi over 3. That's minus pi over 3 there. It's going to stop at minus pi over 3. When did we start drawing these radial arms? What angle is this one right here?
Minus pi over 2.
Yeah, so we're going to start at theta equals minus pi over 2 and stop when we get to theta equals minus pi over 3. And then for the radii, the radius starts at 0, and then it extends out until it hits this curve right here. Well, which curve is that? That is the curve r equals 4 cosine theta, g of r comma theta, r dr d theta, plus, now we're going to do this second region. The second region is maybe a little bit easier for me to draw these radial arms on. So I go to a fixed angle and I extend out a radial arm. So those radial arms are going to start at r equals 0, and they're going to stop when I get to this curve right here. Okay? This curve right here is just the curve r equals 2. It could be some function of theta, but in this case it's just r equals 2. Okay? But what angles did I start doing that at? I started doing that at the angle theta equals minus pi over 3, and stopping at the angle theta equals pi over 3. So that was for our second region. And then our third region is very similar to the first. It's going to go from theta equals pi over 3 to theta equals pi over 2. So again, to Xavier's question, we do have to always start at the lower, the way we develop this, we start at the lower angle and work up to the positive angle. If you interchange that, that would be like changing your limits of integration in a Calc 1 problem. And this integral is not the same as this integral. And so you want to be really careful with that. Now, you could probably adjust things as you wished, but you have to appropriately compensate with minus signs. We're not going to worry. I would just encourage you to always keep these in the right order. And the radial arms, again, for this, start off at r equals 0 and stop at r equals 4 times the cosine of theta. Because, for example, this piece right here, I stopped when I hit this curve right here, which is the curve r equals 4 cosine theta. G of r comma theta, r dr d theta. Folks, it's very important that you draw these pictures. You don't have, notice I didn't even tell you what the function g of r theta was, right? We don't know what that function is. We don't know anything about the surface that we're thinking about living above this polar region. That's not what I mean when I say draw the picture. When I say draw the picture, draw something in the domain coordinate system where you're working with so you're able to easily obtain your limits of integration. Just like I said for those type 1s and type 2 integrals that we were doing before, it's really important to draw your either horizontal, or sorry, that's vertical, or your horizontal stripes. Okay. That was the key, I think, to being able to do integration in rectangular coordinate system. In your polar coordinate system, the key is to draw your radial arms, where you start drawing the radius, where you stop drawing the radius. By the way, we always integrate these. I shouldn't say always. That's a strong rule, but we will typically integrate these in the order of integrating with the innermost integral being r and the outer one being theta. You could interchange them conceivably, but usually we give our functions. We think of if we're just describing a curve in the polar coordinate system, we think of the theta as being the independent variable and r as being the dependent variable. So that's why we almost always do them in this order. Okay. I think what I'd like to do now is let's go ahead and pause here. We'll start up in 10 minutes. So if we could start here at 2:15, that'd be resume the recording. And let's look at number 7 here, which is a nice visual problem to look at. I mean, using the image the book provided. So in this problem, we're told that we've got a region. In this case, it's outside of a cylinder, and that's maybe something a little bit different to this problem. But I do want to talk about when you've got something bounded above and bounded below, when you're building a solid out of that, I want you to think of that as, you've got like two sides of an Easter egg or something like that, and you've got a solid above, a solid below. And so you're going to have to determine the intersection of those two regions. That's what you always have to do when you have, well, I guess always is a little bit strong word, but often have to do with these types of problems. So we've got, in this case, a hyperbolic paraboloid above and a standard paraboloid below, and we need to look at where those two curves intersect. So again, I don't think it would be very feasible to ask you to sketch something like this. Okay, it's nice to have that visualization. I don't think it's feasible to have you sketch something like that. But what I do think is feasible is for you to sketch this region, the domain region in the xy plane or in the polar coordinate system. Okay, and I don't think it's entirely clear just from looking at this image, but it turns out that the intersection of the hyperboloid and the paraboloid also intersect along a circle, and because of that, that makes our domain region R an annulus, and those annuli are ideal for polar substitutions for lots of reasons. Anyway, again, Matthew asked a really great question earlier. These questions are still sort of cooked up in that two things are happening. Both are functions that we're integrating between, in this case between two hyperbolic paraboloid and another paraboloid, both have components of x squared, y squared in them. And their region of intersection is going to have x squared, y squared in it. So these are still kind of cooked up problems in that sense. So anyway, let's go ahead and look at where do these two surfaces intersect. So that's the first question we have to ask. So again, I'm going to continue with this problem, but I'm going to assume that I don't actually know what this graph looks like down below here. Okay, so we're going to ask the question, where do the two surfaces okay, and in this case what I'm going to do is I'm going to set z equal to z. Okay, that's not the only type of substitution you could do in these problems, so sometimes you have to get a little bit clever with these. So for example, what you might do is you might solve for an x squared y squared in this problem, and you might solve for an x squared y squared in this problem, and then set the two x squared y squares equal to each other. I don't know, there's lots of different ways you could go about doing this, but in this case, setting the two z values equal to each other, since they're both already solved for z, seems like the way to go. Okay. So if I set these two z values equal to each other, here we've got our hyperbolic paraboloid, and we're setting that equal to the regular paraboloid. And now if we just do some rearranging of this, let's see what we've got for their region of intersection. And if I go ahead and take these x squares, y squares over the other side, that gives me 2x squared. Subtracting over a y squared gives me plus 2y squared. And if I factor out a 2 and divide it over, we end up with 4 is equal to x squared plus y squared. So again, folks, you're looking at taking advantage of this polar substitution. So you're trying to find a way to describe your region in something that will be convenient in polar coordinates. And that's actually where the hard part of this comes from, right? I mean, after a little while, you really are just following this integral formula that we gave, right? The hard part is getting to that point. And one thing that my math labs, it's come a long ways over the years, and now it asks you to set up the integral, and that you'll find that really helpful, that feature where it says, before you even go ahead and evaluate the integral, let's practice just setting it up. Anyway, so what we now see then is we want to be outside the cylinder. X squared plus y squared equals 1. Again, that's a cylinder in the in 3 space, but if you were to intersect it with the xy plane, its cross-sectional graph looks just like a circle of radius 1. And so if we were to describe this region in the xy plane now, we have that we want to be outside the circle of radius 1, and we want to be inside the circle of radius 2. So this is our annulus region that we also saw when we looked at this picture here, but I think it was a little bit, I mean, you won't always have a picture like that for you. So you want to practice. Again, I'm not worried about actually what is the graph of the, what do these two graphs look like when they intersect each other, and drawing a picture of that solid. But it is important that you draw what its region looks like in the xy plane or in the polar plane. Okay, so once we've got that picture, I think we're ready to go. So we're going to say that the volume of this, the volume formed by this solid, and I'm not going to write the double integral, we'll just say the volume formed by this solid is going to be the integral, and then we're going to integrate over this region R here. Okay, this region R, so this is the region that we just gave. So how are we going to integrate that? We'll integrate from R equals 1 to R equals 2, and then theta equals 0 to theta equals 2 pi. And that's how we can describe this region in polar coordinates. Okay. And then I'm going to go ahead and leave this as a function of xy for just a second. Or I guess we could do the work down here. Let's just do it down below. So what we're going to have is we're going to have the, for the volume, let's draw a little, I guess let's go back to this picture here. Sorry, given to us. So we don't want the volume between, say, this hyperbolic paraboloid and the polar plane, nor between this paraboloid and the xy plane. What we want is the volume between these two, bounded above and below. So that's going to be like one little column in the way that we drew our columns from before. way back when we were drawing our columns above either the XY plane or the polar plane. The column's not going to go all the way down into the polar plane in this case. The column's going to start at the lower curve and stop at the upper curve. Okay? So when we think about what is the height of this column here, we're going to do the upper curve minus the lower curve. And we saw the exact same thing in the rectangular coordinate system. So we're going to do the upper minus the lower. And we were told initially that it was bounded above by this curve, so minus x squared plus y squared plus 8. And we're going to subtract from that the lower curve, which is x squared plus 3y squared. That difference will give me the height of that column there. Okay. And so if we go ahead and if we go ahead and simplify that, that gives me, I think, minus 2x squared minus 2y squared plus 8, which if I write as minus 2x squared plus y squared plus 8, then I'm ready to do the polar substitution on this. So again, I don't always write out, and you don't need to either, let x equal r cosine theta, y equals r sine theta, especially since oftentimes our substitution is to replace x squared plus y squared with r squared. Okay. But if you have any questions about what I'm doing when I do these substitutions, do let me know. Okay, so we can rewrite this as minus 2r squared plus 8 dr d theta. Is that right?
Missing an R.
Ah, missing that factor of r dr. Yeah, so talk like a pirate day or something. R dr d theta. All right. So now we're ready to actually evaluate this integral. So this is going to be the integral from 0 to 2 pi of 1 to 2 of minus 2r cubed plus 8r dr d theta. So I went ahead and incorporated that r into the integrand. And that's equal to the integral from 0 to 2 pi of minus 2/4. I'll go ahead and write 2/4 r to the 4th plus 4r squared, evaluated from r equals 1 to r equals 2, d theta. So we got the integral from 0 to 2 pi, and let's see here. I did this beforehand, so I'm not going to try to do it right now. When I cleaned that up, I ended up with 9/2 when you clean that up. So folks, just in the interest of time, because I often make mistakes, we'll just go with that. Does anyone have any questions how I got to 9/2? Okay. So this gives us then 9/2 theta evaluated from theta equals 0 to theta equals 2 pi. So we end up with 18 pi over 2 minus 0, or we get that the volume of this shape, so you can think of it as this paraboloid intersected with this hyperbolic paraboloid, but then cutting out the cylinder in the center, is 9 pi. So I don't know, 9 pi units cubed. Questions on that example, folks? Again, folks, I don't think you can get anywhere until you start sketching your polar region. Or sketching it in the rectangular coordinate system and then start thinking of it as a polar region. That is the essential part, I think. It gives you kind of your framework to fall back on. Okay, so we're now ready to move on, and we're going to start out on triple integrals today, and we'll have this section and a couple more sections dealing with them. And I'm not going to get all the way through today's section. We'll pick it up on Thursday. At this point, we've developed this story a few times, right? Where we start with a region, we subdivide it into subregions, We take a representative point within that subregion, multiply that to our width or our area, or to, in this case, our volume, and we start developing an integral based on that. So everything is still going to carry over just like before, we just won't be able to draw a picture of it any longer. So now we're going to be looking at a function of 3 variables. So this is a function that the graph would live in R4, so we can no longer envision its graph, right? You could create a computer animation and have time morphing a shape. That's one way to look at it. And I'll give you another interpretation of it here in just a moment. So actually, those are the 2 great interpretations. Well, there's a third one. There's actually 3. Let's just talk about that real quick, folks. 3 real good interpretations of a 4-dimensional function for you are: the first one is to think about a shape, and that shape morphs with time. Okay, that's one way to think about it. Another way to think about it is to think about, you've got a room, a space, a volume, and then at any point, the function outputs the temperature of that point. Okay. That's maybe a helpful way to envision it. And we had that question with our, I think we had a moth or a fly flying around, and we had the temperature, right? So that's one way to envision a graph that lives in R4. Okay. And then the third way that's going to be really useful, and we're going to do that here, is to think of the function as a function that gives you the density of the object at any point in space. So you plug in the x, y, z coordinates and it outputs the density. And I like this one because then the triple integral really has a real clear real-world interpretation. If you sum up the densities at all points inside of a space, then you've got the mass of the object. And that's probably the most helpful way to envision a 4-dimensional function. So, sorry, I should say a function of 3 variables that lives in R4. Okay, so it's got, the coordinates look like x, y, z, w. So its graph lives in R4 here. Okay. So you think of it, you input the space, and it outputs the density. And then if you want to think about what does it mean to be taking an integral over this, you can think about n volumes, the 4-dimensional equivalent of volume, but I can't imagine that. But one way to interpret that is to think about it as the mass of the object, where this value is the object's density. Okay, so again, let's just run through this. How are we extending things? So I said notice this graph, listen. Okay, so we can visualize the domain, though R3, just as we subdivided R into subregions with width and dx to give us the net area between a curve y equals f of x and the x-axis. We also subdivided R2 into sub-whats? We divided into sub-rectangles. So here we had sub-regions. We don't really have a good word for that, but sub-widths. In R2, we divide into sub-rectangles, each with an area, dA, given by dx dy, or we thought it was dx times dy. So here's how we ratchet it up to the next level, and you can continue doing this as long as you want, as long as you get an interpretation for yourself for thinking of it. So now we're going to think of, and that gave us the volume between a 3-dimensional surface and the xy plane. We're now going to subdivide R3. What do we subdivide it into? We subdivide it into cubes, each of those cubes having a little volume dv, where you could think of dv as a small x times a small y times a small z. That's giving you a small volume, the volume of a small cube. Okay. And that will give you, then what we'll do is we'll come up with sort of a 4-dimensional equivalent of volume. All right, so we can't visualize it. It's even difficult just to talk about, but I gave you that interpretation of, or right here, that interpretation of at each point you compute the density. If you were to sum up all of those densities at each point, that would give you the mass of the object. Okay, so we are not going to deal at all with this, so if we call this d f of x, y, z dv. So this is the triple integral. I mean, we'll write it out often, but we're never going to compute one of those on its own. Like I said, what you really do is you take a small cube in 3 space, and then pick a representative point inside that cube, plug it into your function, and you multiply the volume of the little cube times the output of that function for a 4-dimensional version of volume. We're not going to do that. Instead, we'll always just immediately translate them to some sort of iterated integrals. Okay? So how do we think of the iterated integrals here? This is, again, where I think a visualization like this is really, really important. We're not going to often sketch, so I should be careful. Here, you will sometimes have to sketch 3-dimensional shapes in order to think about this. Okay? So here's what I want us to do. I want us to take a point in our xy plane here. Oh, and I should say this. So this integral, this triple integral, is difficult to work with. So we're always going to do it as an iterated integral. Just like for our double integrals, we didn't work with the double integral. We transformed it to a iterated integral as long as Fubini's theorem applied. Same thing's going on here. But with our double integrals, when you had iterated integrals, how many ways were there to integrate? You could integrate with respect to x first and then y, or with respect to y first and then x, right? But if I have dv and I'm thinking of it in iterations of dx, dy, dz, how many different ways can I arrange those 3? Well, there's 3 ways I could choose the first one, 2 ways I could choose the second one, and 1 way I could choose the third one. So there's a total of 6 different iterated integrals here. I'm not going to give you a formula for each of the 6 iterated integrals. But we'll think about developing one of them. We'll give a formula, and then we'll just work some examples. Okay? So what I would like to do is I would like to construct the iterated integral. We're going to be constructing the iterated integral. We'll worry about the limits here in just a second. D f of x, y, z. But we're going to integrate dz, dy, dx. So I'm going to develop this one here for you. And I'm not going to ask you to develop these completely from scratch. Okay. But anyway, you'll see what's going on as we go. All right. So one way to think about this is I'm going to pick an x coordinate and fix it. Okay. And when I pick an x coordinate, I can then think of all of the associated y coordinates in the xy plane with that. Okay. So then inside of that, I'm going to fix one of my y coordinates. So I start with a fixed x coordinate, and that gives me this region parallel to the y-axis, that all of these xy order pairs have the same first x coordinate. So I iterate along that. Then I fix a y coordinate. That's going to give me a point in my xy plane. Okay. And then that's going to, I plug that into, in this case we're going to do between 2 bounded surfaces here, so that's going to give me z values that range between here and here. Okay. So for a fixed x, I've got some slice, and then for a fixed y, I've got now a fixed point in my xy plane, which is very important. This is no longer the domain space. This is completely changed, right? Each one of these variables is now an independent variable. This is how this is different. One of the reasons why it's different from what we were doing before. Okay. But then once you fix an x and a y, you can then allow z to vary between these 2 values right here. Okay. So one way we could look at this is, let's go ahead and sum up for all the z values between here and here. So we're going to sum up between those. So we would have, for this lower, I said that this was bounded between the surfaces h of xy and g of xy. So we've got z is equal to, the lower one is the g of xy, and then the upper one is h of xy. And if we plug all those z values in to this function that we want to integrate over, for some, I'm going to put this x naught, y naught, but don't write that here just yet. Just let me talk about that. Okay. So for a fixed x naught, fixed y naught, we then plug in all z values in between. That's between these two surfaces here. Each one of those is giving us an output, and we're summing them up. Okay. That was for, the way you could look at that is that was for, so give me just a second before you write this down. I'll give you plenty of time to write it down. That was for some point in our xy plane. Now again, that xy plane is not the domain space anymore, but we could think of it as a region, just like we had before. So I could say integrated with respect to A over that region R, where R is the projection of this surface, or sorry, of this volume into the xy plane. So I'm going to go ahead and now put what I want you to copy down here. So we're going to do that over all xy, where xy is in our region R. So this is for all xy. It's contained in our region R. Okay. Now, one way to look at that is, so what have we done? We've taken our surface that's living in, or excuse me, our solid that's living in R3, and we just chose to project it down into one plane. Why? Because, why did we choose to project it down into the xy plane? Because we were given something about the bounds on z in terms of x and y. So it made sense to project it down into the xy plane. Okay. So again, one way to look at that is we first fixed an x-coordinate, and then that gave us this entire swath right here for that x-coordinate. And then we fixed a y-coordinate in there that gave us this entire column, and we summed up the functional values for a fixed x naught, a fixed y naught, and then all z values in between the upper and lower bound there. All right. Well, in this case, in this particular problem, when we're in the xy plane, we choose to view this one as a type what region? What does this region look like to you? And the number's not, I mean, I don't ask you to have the number memorized, but I think we called this a type 1 region before. And you can see that because we've broken this up into a column, or a strip that's ranging from some g of x up to some h of x. Okay. So what we can do now is we can break up this double integral right here into an iterated integral, where the y values are going to range for some g of x. Let me go ahead and put y equals g of x, up to some y equals some upper function h of x of our f of x, y, z. Oops, I lost the z integral. Z equals g of xy to z equals h of xy of f of x, y, z. So the innermost integral is a z integral. And then if we can go ahead and then say we can bound the region R in the xy plane, it's a type 1, and so the upper and lower values are bounded by some g of x and some h of x. That gives us the middle integral. And then for the outer integral, we would have from just x equals, in this case, x is just bounded by these two numbers, x equals a, x equals b. Now folks, when you set this iterated integral up, there's oftentimes many ways you can do it. So sometimes there may only be one way you can do it, sometimes you can do it all 6 different iterated integrals that I mentioned. Okay? What's essential is that your outside integral always has to have fixed endpoints on it, A and B, or C and D, or E and F. It's got to have fixed endpoints on it. Okay. All of this then is going to give us the equivalent of our, let's see, we're not B, D of f of x, y, z, dv. So all of this particular iterated integral, if the, well, first of all, if the underlying function is continuous, if this f of x, y is continuous over the entire 3 space that it sits in, then then the value of this iterated integral will equal the volume of this value of this triple integral. Okay, so what have I just summed up here? If you're able to, and this is the key part, right? So for this is 1 of 6 triple iterated integrals. But you can see, sort of, so don't get bogged down by the fact that it's 1 of 6. Look at how the region's described. You've bounded your z values by some h of xy and some g of xy. That makes it the one that you're going to use as your innermost of the iterated integrals. Okay? And then your y is bounded by some function of x above and below. So that makes the candidate for your middle integral. And then your x is bounded by just real numbers. So if you're able to set it up, if you're able to describe your region this way, then this would be an appropriate iterated integral. This one right here, the integral from x equals a to x equals b, the integral from y equals g of x to y equals f of x, of the integral from z equals g of xy to z equals h of xy, of your f of x, y, z, d what? Well, you're working from the integral out, so this is going to be dz, dy, and then dx. And by the way, I missed the dy and the dx on that one up there. Okay. Now, the key thing is that if all 6 of these, so all 6 of these bounds, here we've got the bounds on x, the 2 bounds on y, the 2 bounds on z. If all 6 of them are numbers, you can integrate this in any order you wish. But if some of them can't be given by rectangular coordinates, like you've got some function, upper function, lower function, or upper lower function in your z, then you're going to have to be judicious in the order in which you do your iterated integral. Yeah, I think I saw a question coming in. Does someone have a question?
I think it's a correction on the
Oh, yeah,
y
please.
integral from g to x to f of x is what you wrote.
Oh, I'm sorry. Yep, I did that
know.
again. That should be h of x. Great. Okay, so let's go ahead and do a triple integral that I've already set up for us. Okay, just to get practice in evaluating this one. Okay. So here we've got an example of a triple integral that we want to evaluate. There's not really, I mean, you can give yourself an interpretation for this. This tells you the density. You give a point in 3 space, and that gives you the density of that object. And so we're computing the mass of it, is one way if you want a real-world interpretation of that. Okay, so let's first talk about the order in which this was given to us. Notice that because, and I didn't write these on here, so you could go ahead and say, this is y equals 1 to y equals 6. This is z equals 0 to z equals 4 minus 2 y over 3. And then this is our x equals 0 to x equals, because this innermost bound here is a function of y and z, so we're bounding our x coordinate by y and z, that's the one we choose to make our innermost integral in the iterated integral. Okay. And so anyway, you'll see when we do another example of this, of setting one of these up, how we make those choices. Okay, but this is not the same integral we computed before, because you can see this one is first with respect to x, then with respect to z, then with respect to y, and that's different than the one we were given. And again, an equivalent of Fubini's theorem applies and says, hey, as long as this function's continuous, almost wasn't. This is from y equals 1. Right, so it is continuous over the over the solid that we're integrating it on. Okay, then this iterated integral would give me the same output as any other iterated integral. Okay? But as far as being able to compute it, this is the way we're going to have to compute it without doing transforming our limits of integration. Okay, all right. So let's go ahead and jump into this. Okay, so for the innermost integral, we're integrating with respect to x. Folks, I found this was really helpful on this problem, and it'll be helpful on other problems. When do I start integrating with respect to y in this case? For my last integral, right? So as far as x and z are concerned, my y is a constant. So let's put that 1 over y all the way out there, just like we could factor a constant out of any other integral. Okay. And so that would just leave us with the integral from 0 to 12 minus 2y minus 3z. If you like, you can put a 1 there as sort of a placeholder if that helps. But then with dx, dz, dy. Okay. I found that was really helpful in this problem to not have to worry about carrying along that 1 over y and having to simplify it with other expressions involving y until I got ready to integrate with respect to y. Okay, so that's a strategy. Again, this just takes a lot of practice. Okay, so that would give us then the integral from 1 to 6 of 1 over y times the integral from 0 to 4 minus 2y over 3. And then integrating with respect to x just gives us x evaluated from x equals 0 to x equals 12 minus 2y minus 3z. And then the next integral is dz dy. Okay. If anyone have any questions about what I just did there? Because I think sometimes in these triple integrals it starts to get a little muddy. Okay. So this gives us the integral from 1 to 6 of 1 over y times whatever this comes out to be, integral from 0 to 4 minus 2y over 3, and then this integral evaluated to be 12 minus 2y minus 3z dz dy. One to 6, 1 over y, integrating this function with right here with respect to z gives me 12z minus 2yz minus 3 halves z squared, and I'm going to evaluate that from z equals 0 to z equals 4 minus 2y over 3, and then the last interval would be with respect to y. Okay. So folks, I'll go ahead and fill this in, and then I'm going to cheat because I did this earlier. We've got 12 times 4 minus 2y over 3 minus 2y times 4 minus 2y over 3 minus 3 halves times 4 minus 2y over 3 squared. And then all of this is integrated with respect to y. It's a little long. Questions on that so far, folks? Okay, so you can check me, but I did double check this. this comes out to be 1 over y times 24 minus 8y plus 2/3 y squared. 24 minus 8y is 2/3 y squared, and then all integrated with respect to y. Okay, and that's just simply what I get when I clean up this big mess here. Okay. So if we finish this up one more time, we get integral from 1 to 6, 24 over y minus 8 plus 2/3 y, all integrated with respect to y. So let's see here, that gives us 24, the natural log of y. Folks, I hope by now that you know that if you're just doing a general antiderivative, you need the absolute value on your y. But you're welcome to look at your limits of integration, and when you notice that both of those are positive values, you don't need the absolute value on there. Minus 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 8y plus 1/3 y squared, evaluated from y equals 1 to y equals 6. And if we clean this up, this just simplifies to be 24 natural log of 6 plus 85/3. Okay, so that was a mess, but we got to see just how this worked with our upper and lower functions being themselves. So the bounds here, what's new here is this bound on x was a multivariate function, right? X is dependent upon both x and y, so that must make this a little bit more, well, certainly gets messy very quickly. Okay, so let's go ahead and look at a easier example, and this is one where I want us to start feeling pretty comfortable now. So if you have questions as we go through this, please feel free to interrupt me. All right. So this actually takes that viewpoint of thinking about these triple integrals as integrating some density function and having it output the mass of the object. So in this case, we're given a region D, and D is about as simple as it gets. This is all nice. It works really nicely in rectangular coordinate system. We're told we're in the first quadrant, or excuse me, first octant. Okay, everyone's good with octant, right? You take your X, Y, Z plane, you can divide it up into 8 regions. This is the one that we always sketch, usually, or we don't always, but we often sketch this one. Everyone okay with that? Okay. And so we're told that we're going to, it's bounded by, in the first octant, bounded between x equals 0 and x equals 3, so 1, 2, 3. And then y equals 0 and y equals 3, 1, 2, 3. And then z equals 0 and z equals 1. So we could imagine this is our solid here. And that's about the best I can do, sketching it. Okay, so we've got a solid box, it's like a brick. A paver or something like that. But this is a special paver in that the density of the paver depends on the height of this paver. So at any point, your density is 2 minus your z coordinate. Okay. So we want to go ahead and set up some sort of triple integral here. Okay. So what I want to say is that any of the 6 iterated integrals triple integrals will work. Okay, so why is that? Why am I saying that?
Because they all have definite bounds.
Because all of their bounds are given by, yeah, definite bounds. That's a great way to say it. Good. So we didn't have, you know, maybe this wasn't some, this up here wasn't some parabola region or something like that. Okay. So that means that it doesn't matter. Now, if this had, say, maybe this was a parabola region and maybe this was, you know, this was some region like that, we'd have to be careful, and we would have z be our outermost integral, because the z one is the one that has fixed bounds between z equals 0 and z equals 1. Okay, so you always have those functions that are, those bounds that are given by functions sitting inside, nested appropriately. But in this case, it doesn't matter how you set it up. So we'll go ahead and just set it up. I'll integrate with respect to x, then y, then z. Okay. So we can go ahead and set this up. We've got the integral from, so I wanted to start x, y, and z. So my innermost integral is going to be with respect to x. So that's from x equals what to what? Well, x equals 0 to x equals 3 of our f of x, y, z dx. And then y is going to range from y equals 0 to y equals 3. So there's our dy. And then our z is going to range from 0 to z equals 1. And that's going to give me dz. Now, this was probably actually not the best choice. How come? Well, there's a whole bunch of choices that are being made as you do this. In looking at this function is not going to be hard to integrate no matter which order we do it in. Right? It's not one of those that's going to have to, if we integrate it one way, we have to do integration by parts, but if we integrate it another way, maybe we'll get around having to do integration by parts. Okay? Or if we try it one way, we'll have an impossible integral, one that we can't do without using power series or something. But if we integrate it the other way, it'll come out smoothly. Okay? In this case, we're not going to have any trouble integrating this no matter which order we do it in. But I would think that you would probably actually want to start in with z first, integrating with respect to z. How come? Because after the first time you integrate it, you're going to have a number. And it'll just make everything a little bit easier to work with. Okay. Now, folks, so let's go ahead and set this up. 0 to 1, 0 to 3, 0 to 3, and then we'd have 2 minus z dx, dy, dz. Notice, folks, if you don't write the x equals, you got to make sure, I mean, the order here is critical, right? So so be very careful with that. Okay. Folks, can I factor that z all the way out like I did before? Like in the problem before, I said, oh, let's forget about this y for a little bit. Let's just pull it all the way out to where we start integrating with respect to y. Can I do that here?
No.
No, I cannot. And the reason why is that z is not a constant times the number 1. Z is an expression sitting inside of this, and so you cannot factor that out. So be careful with that. I know you guys are very good at pulling out constants and whatnot, but this is a new environment for you, so be careful. Okay. So anyway, if we integrate this with respect to x, 0, 1, 0, 3, if we integrate with respect to x, we'll have 2x minus, actually, I'm going to do it this way, 2 minus z x, evaluated from x equals 0 to x equals 3, dy, dz. Okay. And then evaluating this would give us, notice that the lower one will vanish, so we get the integral from 0 to 1, 0 to 3 of 3 times 2 minus z dy dx, oops, excuse me, dy dz. Integrating now with respect to y is going to give me the integral from 0 to 1 of 3 times 2 minus z times y, evaluated from y equals 0 to y equals 3, dz. And evaluating the upper and lower limits there gives us the integral from 0 to 1 of just 9 times 2 minus z dz. Now I can pull this, and I could have actually, I guess I should have said that, I could have pulled this 3 out from the get-go, all the way out to the end of the problem. And likewise, I could have pulled it out here. I'll go ahead and pull that 9 out to the end of the problem. I can't pull that 2 out, right? That's part of the expression. I could factor a 2 out of both terms and then pull it out. Okay, I think you guys have it. So anyway, this would give us 9 times 2z minus 1/2 z squared, evaluated between 0 and 1. And so we've got 9 times 2 minus 1/2. And then we'll just put minus 0. So that gives us 3/2. Is that 3/2? Yeah, 3/2 times 9, or 27/2. Questions on that, folks? Okay. Now, when we're integrating over a function, we've got actual, an actual f of x, y, z is some function other than 1. I think it's very hard to imagine what's going on here. Again, what we're really doing is we're taking a cube in 3 space, taking a representative point from within that cube, evaluating the function at that point, multiplying it to the volume of that little cube, and then summing that up over all cubes in our space. That's what we're doing when we do a triple integral. But I can't even look at that, so it's hard to get an interpretation of that. I think that your go-to interpretation, as I said, is this density idea. But if our innermost integral, and this should be a triple integral here, if our function is the function f of x, y, z equals 1, then evaluating the triple integral, and folks, I'm sorry, the command I have to type for this is I, N, T, and it's very easy for me to miss an I on that, so I apologize. That should be a triple integral there. But anyway, just like if we take the double integral over the function 1, that gives us the area of our region, whether we're in polar or rectangular coordinates. The same thing is true here. If I take the triple integral over the function 1, that's going to give me the volume of the space, of my domain space, D, my region D, which sits somewhere in 3 space, right? So again, our domain, this is why this is really hard to imagine. Our domain itself is 3 space. Those are the domain values. This is our domain here. The graph, it gets mapped to something that lives in 4 space, which we can't really imagine. But if I think of the function f of x, y, z equals 1, which is a function whose graph lives in R4, technically, then I can go ahead, when I evaluate the triple integral, it's simply going to give me the volume of my domain space. So this is another way of computing volume. Okay. Let's see here, where are we? Yeah, that's fine. Okay. So let's go ahead and look at this prism here, which we've got bounded by the plane z. So it's in the first octant and also bounded by the plane z, and 4 minus 2x is equal to y. So let's see here. So if I'm thinking about just so here's xy, here's z. If I'm thinking about just the xy plane here, so I'm just thinking about the xy plane, this would be the line 4 minus 2x. So let's see here, that would have a y-intercept of 4 and an x-intercept of 2. So that's this line right here in the xy plane, but that's going to give me then this plane in 3 space. Okay? So that's going to be one side of it, and then I've got the plane z equals 6, so maybe here's where z is equal to 6, and so then that's going to give me this plane right here. And what have we got? Well, we've got a mess. Okay. But let's go ahead and see if we can't redraw this now that we've got a sense of what it looks like. So let's see here. Let's So let's imagine this looking something like this. So now there's just a resketching of that. So this is still x, this is still y, this is still z, and maybe I should have done a different color here, but that's the intersection of the first octant with those other two planes. So folks, when you do it, so this is where you are going to have to sketch some three-dimensional shapes. Because what I have to do here, just like I did in R2, when I said, oh, you know, maybe this is our upper curve and this is our lower curve, and then we said, okay, let's think of this as a type 1 integral. We're going to have to do the same thing with a three-dimensional drawing here. And that's a little bit confusing. Okay? Now, in this case, we've got two different options, or actually three different options here. Or actually more options, but we've got three options that are kind of readily available to us. So let's see here. This is where x is equal to 2, and this is where y is equal to 4. And this is where z is equal to 6. But one option for setting this up is to integrate from z equals 0 to z equals 6. Okay. So right now what I'm doing is I'm saying pick a z value. Okay. When I pick a z value, for some z value, that's going to give me a cross-sectional plane here for that z value. Okay. So then let's go look at that cross-sectional plane. This is some z equals z naught plane. Sorry, I shouldn't draw that in green. Let me draw that in blue here. Okay. So that's some z equals z naught plane, and we've got this slice of that prism, that piece right there coming through it. And now what do we want to do? Well, we want to pick how the x and the y are going to run. So I think what we want to do is, let's go ahead and, since this is given to us as a function, y is a function of x, I think I want my innermost function, my innermost integral, to be integrated with respect to whom? What do I want the innermost one to be integrated with respect to?
Maybe to x.
I could do that, but if I chose to do that, let's go ahead and set that up, Hosanna. If I chose to do it that way, I would do this from y equals 0 to y equals 4, and then I'd have the integral from x equals 0 to x equals, and then I'd have to solve this for x. And which isn't that bad, I could do that, but that would give me, if I solve that for x, that would give me y minus 4 minus 1/2 y plus 2, I think.
Oh.
Right?
So it's y equals, so y would be better.
So I think it would be better to go with integrating with respect to y as the innermost one. So I'm going to go ahead and change that. So you could do that. In this case, it's not really that hard to change that around. But I think that as the problem was originally given to us, we should integrate it first with respect to from x equals 0 to x equals 2, and then integrate this from y equals 0 to y equals 4 minus 2x. So the way we think about this is in this new plane now that we sketched, if this is x, this is positive x here, and this is positive y here. Once we fixed a z value, then we go out to some x value, and then we're going to integrate between here and here, which is between the y value 0 and the y value whatever it is when we hit that curve. So what's our function? If we're just looking for volume, folks, what's my function here? It's just the volume finding function 1. And you don't have to write that. I probably will just keep doing it for a while. And then we're going to iterate dy, dx, dz. Okay. So where are we? We're about out of time. So we'll stop there.